You're welcome.
Okay, everybody, welcome. Thanks for showing up. This is the Howard Astronomical League monthly meeting for June. And we have a pretty cool meeting, a very good speaker, and it seems like we've got lots of people online. So I'm very excited to get started. So first things first, here's the agenda for tonight. Go through some introductions, make some announcements, and then we'll hear from our speaker, and then our regular feature of what's out in the sky this month. We'll have Phil, Jim, and Wayne talk to that, and then we'll go through some astro images and sketches. Although given the smoky cloudy skies that we've been experiencing, we don't have too many of those, but I'm amazed that people got anything at all. Anyways, introductions. If there's anybody who's new to the club and on the call and would like to say hello, and please unmute and say hi. You don't have to, but if you'd like to.
Yeah, hi. My name is Richard Taby, and I'm hoping to join the league. I have sent in my application and my check, and hope to hear soon.
Terrific. Yes, I'm sure you will hear soon. As soon as somebody checks the mailbox. Welcome. Are you have you been involved in amateur astronomy before? Or?
Yes, for quite a few years. I've been members of some other societies over the past few decades, but I haven't been a member of one, I'd say, in the last 20 years or so.
Okay, well, don't worry, the technology hasn't changed at all. Yeah, well, I hope that you are able to make it out to some of our events and get to know some of the other members, and you know, get refamiliarize yourself with all the new gizmos that are out there. Welcome.
I'm looking forward to that.
Terrific. It's a good start. We have a members only star party tomorrow, this weekend, and then a public star party the next week. Those would be good places, good opportunities for you to start to get in touch with the folks and dive in. Anybody else? Okay, well, I think I'll just move on then, and a couple of announcements. So this is for you. It's Richard.
Yes. Hello.
Yes. So June 17th, members only star party. This is our observatory at Alpha Ridge. We got lots of people who set up their scopes right outside. Members party, usually people are just kind of checking out their equipment, but there's usually a lot of, everybody's willing to talk and socialize and talk about their gear and whatnot too. Then June 24th, the next week after that, we have a public star party where there will be members of the public, and people will be setting up their scopes and sharing views of the night sky. Inside the observatory, we have a big scope on the mount with a camera connected to it, and we kind of live stack some images of something and can share those views with people on the screen. So that should be happening the next weekend on the 24th. I think
very interesting.
Yeah, I think David Stein is on. He'll be one of the hosts next, not this weekend, but next week. Okay, so that's star parties. There's a lot of regional star parties. If you feel inclined to find that link or look at the slides afterwards, when they're posted to the website, there's all sorts of information about the upcoming larger star parties, like in the Grand Canyon and all that are coming up. Another event that we have that HAL will be participating in is the Robinson Nature Center has a summer solstice event, and you can pay $10 and go inside and do some of the activities that they have inside the observatory, or you can not pay $10 and just hang out with HAL on the porch there. There'll be several people with their telescopes. So it's from 2 to 4. HAL members are probably, should probably show up a little bit earlier than that to get set up. And I know we have at least 3 or 4 people who've already signed up to or indicated that they're planning on going. Daniel, did you have something to say?
I guys, I was looking out at the sun straight ahead of me, and it's red. It's not bright yellow, but it's red. So with that, that tells me there's still haze from the wildfire outside.
Yep, there sure is. It's been a rough go this last month or two.
I'm sorry.
Really hoping that. Sorry.
Can you repeat that one more time? What did you say about last month?
Yeah, I think the smoke has been very, very terrible for our hobby and for breathing on some days over the last month. But we gotta, hope for those wildfires to get under control. And but this forecast for the next few days is still not very good.
Yeah. So yeah, did you guys see the red sun outside?
Yeah, sure. And we'll be able to see it. In fact, there's at least one picture where somebody got a really nice view of that. Okay, so
well, thank you. That's all.
Okay, let's move on. So the summer solstice event is coming up, and the next thing coming up is Astro School. Do you want to speak to this, Phil, or is Bob Savoy on?
We're both on. So I saw you, Bob. There you are. Yeah, Bob and I are the hosts of Astro School, and I'd like to take this opportunity to make sure that we recognize Bob for all the hard work he put into doing the planetarium show. He did a special on Saturn, right, Bob? And then James Webb Space Telescope.
Yes.
It's been great, and people have all enjoyed his presentations, and it's great. And just so everybody knows, if there's a topic that you would like to cover in Astro School, let me just explain for 1 second. For those of you who don't know what that is, Astro School is a special program that we run here at HAL. It's run on the second Thursday of every month, only in person at Robinson Nature Center. And there'll be different topics, but if you have a topic that you'd like to cover in anything that's related to astronomy, just let us know, because we're not going to be the presenters all the time. Obviously, somebody wants a deep dive presentation into imaging and processing, we're going to have another member who's an expert or even an outside person that would do that. So when it's from 6:30 p.m. to 8:30 p.m. at Robinson Nature Center, the second Thursday of each month, unless you see a cancellation notice. So that's what the school is all about. And if there's anything that you would like to see a class on, even right here during this call, just put it in the chat and we'll capture it, and then we'll get back to you, because we were always looking for topics that you're interested in. So for the next, in July, what we're going to be doing is I'm going to give you a little teaser today when we get to the solar activity session here after our guest speaker, and but we're going to do a deeper dive into the features and details about the sun that you could actually observe, and we're going to do that on the second Thursday of July. And then a couple weeks later, because I'm not available that weekend because I'll be going on vacation with the wife, but a couple weeks later, we're going to hold a special outdoor solar session at Alpha Ridge outside the observatory on in the early afternoon, and invite everybody to bring out their solar scopes. And we're going to do like a several-hour Astro School outside live is a workshop. So look at the class in the 2 Thursday as giving information, and then we'll go into the laboratory a couple weeks later outside. So that's the plan. Victor, or anybody, if there's any questions, Bob and I are here to answer them. If not, back to you, sir.
Terrific. Thanks. I wanted to mention something that just occurred to me before we move to the next topic, and that is that just speaking about the Robinson Nature Center, right now the plan is that we're going to go back to the hybrid. For a while we've been on Zoom since COVID, really. And before that, we just used to meet all in person at the Robinson Nature Center at this same time, the the third Thursday of the month at 7 p.m. So not next month, but the month thereafter, we are going to begin a hybrid meetings. And so we'll still keep the Zoom component. We'll get set up in the Robinson Nature Center with Zoom, and you can join with Zoom if that's how you prefer. But if you want to come and meet in person and kibitz and schmooze, whatever, you're welcome. So there'll be more announcements about that coming up soon. But stay tuned. Next month, regular Zoom, and then the month after, August, we'll start again. Crystal?
Yeah, so I promised that wasn't a planned segue, but as a teaser, here's a book of the month related to the sun. So this month I chose this book here, The Sun Observer's Guide by Pam Spence. This particular version was published in 2004 by Firefly Books, and it is a great book. This book offers people of any experience level just a really straightforward guide to how to observe the sun safely. It gives a ton of relevant information about the structure of the sun, equipment options, how to interpret your observations and sketches. So I've never been a big person on like drawing things that I'm observing, but I think this little handy book here at under 160 pages has really convinced me of the value of actually sketching a projection of a solar image, because it's a great way to really find features like sunspots and prominences and spores and things that I wasn't as familiar with really come to light when you take the time to observe in great detail. It's a lot easier to just take a snapshot or record, a 30-second video, but I think you miss out on some of the experience going kind of old school and going back to how do you sketch an image of the sun and getting really to appreciate the features. And the book does a great job of keeping it very simple, gives you lots of explanations and diagrams and pictures to kind of help guide you through how to do everything safely. So highly recommend. It's a nice, tiny little book, under 160 pages, super beginner friendly. And if you're just getting started with solar astronomy, it's a great way to just get you into it. I will say my one disclaimer is that some of the information is a little outdated since this was in 2004, but the information that's specifically outdated is like the camera recommendations, because, they're recommending 35mm film. And I'm like, yeah, it's probably not as relevant in 2023. But if you're interested, great book, great start to solar observing.
And I
Thank
second,
you.
I second what you say.
Awesome. Hey, Crystal, as long as your microphone is unmuted again, do you want to say anything about, and we're making announcements, do you want to say anything about your observatory?
Sure. So for those of you who are not familiar with me, I'm a HAL member that is transitioned to becoming a librarian, but I also work at Glenelg Country School, and we too have an observatory. I'm actually in my warm room at the moment. It's a little messy, but I'm having an event tomorrow night, which is likely going to be rained out, unfortunately. But my observatory is almost a sister to what you'll see at Alpha Ridge. All my events are open to the public. I don't do any type of virtual component, so it is come in person, bring your equipment, chat, and a lot of it is students and families who are just interested in astronomy, but haven't ever seen an observatory before. So it's called the Gould Observatory on our campus. Everyone's always welcome to our public events. I have one scheduled for tomorrow, fingers crossed that the rainstorms hold off, but not looking so good as of right now.
So do you think it's going to cancel?
I don't cancel mine. So what I do is I run little events. So like I'll have activities like assemble a Galileo scope, or right now I'm working on something with like explaining solar spectra with like Easter eggs. I know it's weird, but trust me on this. So I do host activities and videos and demonstrations for kids and people who are interested, even if it's cloudy. If it does call for thunderstorms or like we're going to get really rained out, then I would cancel. But I really do try not to cancel them unless it's like going to be severe thunderstorms.
But if it's rainy and it's cloudy, then what do you do if it's not canceled?
Yeah, I don't open up the dome if it's cloudy, if there's nothing to look at. But I will run my demonstrations and tabletop activities. So you could still
Hey,
come to
Daniel,
socialize and hang out.
Daniel, there was an email sent out to the club with more information. So check your email if you think you can, you want to make it there.
Hey, thank you.
Thanks, Victor.
Okay, so moving on. It is now time for our auspicious speaker. And I would like to see, I'm very, very ill prepared. Wayne, would you like to say anything about? Maybe not. I'm putting you on the spot.
Yeah, I'm less prepared than you are.
Well, I'm totally unprepared tonight. I'm having trouble with
Okay,
my.
I can just start.
Well, I'd like to introduce you with and give a little bit about your background and I'm having my browser is being weird right now. Sorry, folks. Okay, so our speaker tonight is sorry, very, very slow. Dr. Jay Anderson, who works at the Space Telescope Science Institute with Wayne and Wayne's wife, or where used to work, where Wayne and his wife used to work. He's an observatory scientist, and he has been there since 2007. He has a BA in physics and French from Rice University, a PhD in astronomy from UC Berkeley in 1997. He was working on a postdoc there with grant money and is currently, again, since 2007, been at the Space Telescope Science Institute. And his talk tonight will be the first isolated black hole. So with that, I will let you share your screen and take it away.
Okay. I think someone needs to stop sharing and then I can share.
Okay, go ahead.
Okay, here we go. Let's see. PowerPoint. Share. So do you see the right screen? The correct
We
screen?
do.
Good. Okay, great. So I'm going to talk about the first isolated black hole. People have been looking for this for a long, long time, and we finally found it. My collaborators on this are Kailash Sahu, who is actually the PI of the program. I do the technical measurements, and he's the visionary. And Stefano Casertano, Andrea Bellini, Peter McGill, and several other people have worked with me on this. So in this talk, I'll talk about 5 different things. One is the advantage that Hubble has. I'm sure that most of you guys know a lot of the stuff that I'll say, but I always find it helpful to hear stuff I already know from other people so that you get a different perspective on it, and maybe you can explain it to other people better or differently. And the second thing I'll talk about is my expertise, which is PSFs, which is point spread functions, which has to do with star images of stars and images, and how you can measure them well and how you can use them. Then microlensing in general, and then a white dwarf project involving microlensing, and finally the black hole project. So the advantage that Hubble has is that it's above the atmosphere, so it doesn't have to look through the atmosphere to get to the stars. And when I talk to non-astronomers about this, I say it's like trying to look at the drain at the bottom of a pool with the water in the pool. The water is always moving around, and you can't really see the drain very clearly. Here's a picture of my dog they have a dog swim, and you can see that the lines just look very curvy, even though they're straight lines. But if you were able to drain the water out of the pool, you could see the drain very clearly. Sometimes it's ugly, sometimes it's not what you want to look at, but at least you can see things clearly. And that's what Hubble is able to do, because it goes above the atmosphere and it can actually look at things clearly. And one of the reasons it's so good isn't just that things are sharper, it's that if you look at something from the ground and it's a big image of the star, it's an arcsecond in size, say, then it has to share the light with an arcsecond worth of background. But if you're able to shrink the star size by a factor of 10 in each dimension, then it only shares background with 1% as much background. And so you can really get a lot fainter. In addition to having a more precise view of the universe, you can actually observe much, much fainter with Hubble than you can from the ground, because each star shares less real estate with the background, which is also a source of noise. So this is Omega Centauri. It's the biggest globular cluster. I cut my teeth on globular clusters, so much of my early science had to do with globular clusters. The very first image that with C3, which is the newest instrument on Hubble, which was put in 2009, they haven't been back there since then. But this is the early release image of with C3, and it turns out that they didn't intend for this image to become public, but it's actually one of the most iconic images that was taken with C3. They took it so that they could calibrate the distortion in the telescope. The telescope had actually a pretty bad fisheye lens, and so stars, the picture you get doesn't really map directly to space because they want to have as few reflections as possible to preserve the light. Then they end up just allowing the star images to go wherever they go and then correcting them later with software. So they have to take an image of the sky and sort of rectify their telescope optics. But it turned out that this image was so pretty that they decided to release it almost immediately to the public to show what a good job the telescope was doing. So this is, again, the cluster, and this is the center of the cluster, and you can sort of see that this is such a big cluster that the center looks pretty flat. So let's see, the actual field that we were looking at is the red box here. So it's not exactly at the center, but it's pretty close to the center. And so you guys probably know all of these things. So this is part of what I give when I give a public talk. But the way digital cameras work is that they have a CCD, and like every fourth pixel is covered with a red filter, and every fourth pixel is covered with a blue filter, and then the rest of them are covered with a green filter. And then they're able to combine that with software to give you a color picture. Well, Hubble can't take multiple pictures at the same time, but it can take one picture and then it can change the filter and take another picture. And that's how they make color images with Hubble. Webb actually has a splitter, so it's able to actually observe in two different wavelengths at the same time, so it can make color images immediately. The central field, this is the central field of Omega Centauri. They combine it, like I said, by taking a blue picture and a red picture and putting it together. So here's the blue picture and here's the red picture. And you can sort of see that when you put them together, you get a central field. Now, one of my involvements in this, in addition to trying to do some of the calibrations, was that when they made an IMAX to show off the Hubble repair mission, they had an IMAX camera up in space and they wanted to show some of the images. They didn't want to show the repair mission in 3D and then not show any of the images in 3D. So they needed a way to show the Hubble images in 3D, but they're really just two-dimensional things. And when you look at a cluster, you don't know which stars are closer to you and which are farther from you. That's the hardest thing to measure. So they wanted me to simulate a cluster that in 3 dimensions. And so in order to do that, I had to take this image and break it apart into individual stars. And so I could simulate it. And then when I simulated it, I could put some stars in the close layer, some stars in the middle layer, some stars in a far layer. And then I could simulate it that way. And if you saw the IMAX movie, you actually saw this image in 3 dimensions because of that. So here's the real image, and here's my simulation of it. So one of my expertise is that I do a very good job modeling what stars look like in images. That allows me to measure precise positions and precise fluxes. And when you do that well, you can do some very interesting science, like I'm going to be talking about. So here's another close-up of the central region. And let's see, the colors are so extreme because if you look at the red image and the blue image and blink them, it almost looks like you're looking at a different star field. So a lot of times when Hubble makes these pretty pictures in color, the colors that you see in the images aren't the real colors that your eye would see. They have infrared colors and they have ultraviolet colors, and they sort of have to put it all together. And often they stretch the colors to show off, things that are different. But in this particular case, they didn't have to stretch anything because the red stars have almost no blue light and the blue stars have almost no red light. So it's very, very impressive. And so you might have seen this demonstration before, but when I first put this together and realized that I could simulate star images, I thought, wouldn't it be interesting if I could simulate what astronomers do? So what astronomers do when they look at this, they like to sort of order stars by color. So let's put the blue stars on the left and the red stars on the right. So if you do that, you see that you have a few really bright, really blue stars, a few really red stars, and most of the stars are in the middle, sort of half blue, half red. And the astronomers also like to sort stars by brightest and faintest. So let's put the bright stars on top and the faint stars on the bottom. So you see this end up with a color magnitude diagram just by sorting things by brightest and faintest and reddest and bluest. And so this automatically just comes straight out from the image that you see. So all the different parts of the colorimetric diagram, the main sequence, the subgiant branch, the red giant branch, horizontal branch, and then the white dwarfs. This shows you the lifetime of a star. Now, stars don't move all the way up from the bottom to the top, but the top just peels off as time goes on. But this shows you a nice, and so when you look at the image, you can sort of look at the star, see how big it is, see what color it is, and you know exactly where it is. So this is a kind of a nice public outreach thing that came from the fact that I had to simulate the image for the IMAX movie. So the next topic is going to be microlensing. So microlensing is not a new idea. In, I guess, the early 1800s, Soldner said that they realized that light had a finite speed. So they said that if light is moving around an object, it will get bent by the object, probably. And he figured out how much it would be bent. And it turns out that he was off by a factor of 2. Then someone else said that if 2 stars were lined up, then an observer would see a ring around 1 star. And then in 1915, Einstein came out with his paper on gravitational general relativity. And he predicted that, light would follow geodesics, just like everything else would. But he didn't go into too much detail about microlensing. He actually said it wasn't probable. I'll show you this later. But finally, in 1936, some guy ended up like twisting his arm and saying, I'd really want you to put out a paper about microlensing. What would happen there? And so he wrote this 1-page paper to Science magazine. And basically at the front of the paper, he says, some time ago, R.W. Mandel paid me a visit and asked me to publish the results of a little calculation I did at his request. This note complies with his wish. So I'm just writing this paper to make this guy happy. And then later in the paper, he says, of course, there's no hope of observing this phenomenon directly. First, we scarcely ever approach enough. We never have 2 stars exactly lined up to allow us to make this measurement. So even though theoretically we would see this, nobody's ever going to be actually able to observe this. But it turns out that there are a lot more stars in the universe than Einstein knew about, or even more observable stars than he knew about. Telescope quality gets better, and you look at places that have a good chance of overlap between stars. And it turns out that we've observed microlensing quite a bit. But he did make a good prediction. So just another historical perspective. After the paper was accepted in Science, Einstein wrote to the editor and he said, just between you and me, let me also thank you for your cooperation with this little publication, which Mr. Mandel squeezed out of me. It is of very little value, but it makes the poor guy happy. So that was Albert Einstein on microlensing. So, it turned out lensing actually ended up being something important to Einstein because it was one of the very first proofs of his theory of general relativity. The conventional wisdom was that when there's an eclipse of the sun and you can see the stars that are right, just barely not behind the sun, you can't normally see them in the daytime because the atmosphere is so bright. But during an eclipse, you can actually see the stars that are very close to the sun. And Sir Arthur Eddington went on a mission because he knew when there was going to be an eclipse somewhere around the southern tip of Africa. And he went there in a ship and he took a picture of the sky behind the sun. And he figured out that the stars that were close to the sun ended up getting displaced because their light was bent. And so it turns out that the deflection that Einstein predicted was 1/2 the deflection that was predicted by just doing ray tracing if you assume the speed of light going around it. So general relativity is not, you can't just get it by extending regular physics. And so Einstein was like lauded as a hero because he had predicted this at the beginning. But other kinds of microlensing, he said, just aren't very practical to think about. One of the things that I'll talk about is using microlensing to measure the mass of a white dwarf. So the bigger the sun is, the bigger this deflection is going to be. Now with a white dwarf, you can look at a star that's way behind the white dwarf and see that its position is bent by the location of the white dwarf. And so it appears to come to us from a position that's very different from where we observe it, where it originally was. So we observe it to sort of be a little farther away from the white dwarf than it actually is. And the effect that we're looking for is about 1,000 times smaller than what Eddington was able to measure. So microlensing, here is a graphic that shows you what happens. So this red dot here, I'll show this movie again a few times, but this red dot is a star that's in the middle. So we're here, this red star is in the middle, and then there's a green star moving behind it. And if that green star is exactly behind the red star, then you'll see a ring. But if the green star is offset a little bit relative to the red star and it just comes close to it, then you'll see something different. Let's look at this. So you'll see two images of the green star. The blue things show you the images of the green star. And so you'll see one image that's brighter and another image that's fainter. And one image goes outside of the circle and the other image goes inside the circle. And so it turns out that the average location of the blue images, which are the images that we see of the green star, there's a shift relative to the location of the green star. And so if you can measure the apparent location of the green star over time, you can measure the microlensing shift. And on the bottom, it shows you the amplification. So as the green star gets close to the red star, it turns out that we get more light from the green star, because a lot more of its rays are bent in our direction. And so microlensing events are identified by the fact that they get brighter. And then when you measure something that gets brighter like this in a very specific way, you can go back and try to measure the astrometric signature of it. So
Can we ask questions while you
feel
go?
free. Yeah, feel free.
So what is the meaning of that circle? I didn't follow this. The
Okay, yeah,
circle.
the circle is called the Einstein radius, and it has to do with basically the region around this star where light is bent in a significant way. So it's not an actual physical region around the star. It has to do with where we are relative to the star and how massive the star is. So something that is very massive will have a very large Einstein ring. Something that's not very massive will have a small ring. But it has to do with how far away the star is and where we are. So basically, it basically says something that's within that circle is going to be significantly affected light-wise by that intervening star.
So in this image, is the observer at the bottom of the circle?
No,
At
the
bottom of the
observer is where
screen?
you are. The observer, we're looking at it. This is the plane of the sky. This is the plane of the sky. So this is what you see. If we had perfect resolution of everything, you would actually see these two images of the green star. The blue images is what you would see of the green star if we had perfect resolution. But in reality, this whole region that I'm showing you here all falls within 1 pixel in most detectors.
Okay. Thank you.
Sure. So, and these are figures that show, and the amplification can be a factor of 2, it can be a factor of 100 or so. And the time that it can take for this event to happen has to do with how fast the background star is moving relative to the foreground star, how long the background star stays within that circle. So that sort of tells you how long the event is going to last. So microlensing that we've been doing with HST involve 2 different things: isolated white dwarfs and isolated black holes. Now, the reason isolated white dwarfs are interesting is that we need masses for white dwarfs. It's hard to measure their masses, and especially hard to measure isolated white dwarf masses. Usually, if you try to measure a mass, you're in a binary system and you measure the period and you measure the distance between them, then you can measure their mass. But if something's isolated, it's very hard to measure its mass. So this allows us to, and it turns out that things that are in binaries probably have different evolutionary scenarios than things that are isolated. And so you'd really like to understand how isolated white dwarfs evolve, because that's sort of, you're able to answer more physics questions that way. But when you have, you're looking at isolated white dwarfs, both stars are visible. Both the lens, which would be the white dwarf, is sitting close to us, and then there's a star that goes behind it that ends up having its light bent around the white dwarf, and that's what allows you to measure the mass of the white dwarf. But in the first case, you can see both stars. In the second case, with black holes, you have a star in the background and you have a black hole moving in between us and that star. You can't see the black hole, but the black hole causes the light from the other star to bend around the black hole, and that changes the light that we get from the other star. And if we can measure that change, then we can measure something about the black hole. And it's very hard to measure isolated black holes. That's the same thing with white dwarfs, but even harder to measure find an isolated black hole, much less measure its mass. White dwarfs, you can see them. You can measure them. You can look to see if they have a partner. Lots of isolated white dwarfs are known. Very few. This is what I'm going to tell you about is the very first isolated black hole. Because how are you going to see an isolated black hole, right? it might have gas around it, but then it's not isolated. It might have a partner, but it's not isolated. So in that case, you see one star going through this lensing thing, but you don't see the thing that's causing it. So the challenge in making these observations is that it's hard to get time on Hubble. And Hubble is the only thing that can observe the kinds of precise positions that we're talking about here to measure the full microlensing event. From the ground, you can see things getting brighter and fainter, but you can't measure the positions that you need to measure if you want to pin down all of the microlensing information. Also, you need multiple epochs. A lot of these events, especially for the massive ones, take 3 or 4 years, maybe 10 years to go from before the event, during the event, and after the event. And so you need multiple years worth of Hubble data, and Hubble really gives data out 1 year at a time, maybe 2 years at a time. So you have to have a good strategy to get multiple sets of data. And there's another issue is that what I call the name that tune issue is that you want to make the observation as quickly as possible. So you don't want to get 100 data points because they're not going to give you 100 different observations of it. So you have to be able to say, I can make this measurement in 7 observations. I can make it in 4 observations. And so there's a competition to see how few observations you need. And some people think, oh, I don't need 5, I can do it in 4. And then data becomes public after a certain amount of time. So other people can start running with your data before you get to analyze it. So it's somewhat complicated. So I'll talk real quick about the white dwarf. So this is just a color magnitude diagram showing the end of the white dwarfs. And basically this bunch of stars up here are their bright white dwarfs that are still cooling, but there's a radius relationship, mass radius relationship with white dwarfs. And people really need to be able to measure that to know if you have a white dwarf of 1 solar mass, how big is it? Physics predicts a certain size for it. And so the question is, how big is it so that we can test physics? And there are a lot of bright white dwarfs that we know the masses for because they're in binaries, but we don't know a lot of faint white dwarfs, and we don't have very many at all isolated white dwarfs. So that's why we'd like to use white dwarfs to measure microlensing things. So this is the first program that I'm going to talk about. I'll talk about 2 programs. So somebody went through the Gaia catalog and looked at all of the stars. They found all the white dwarfs and they found all the other background stars. And they tried to find occasions where a white dwarf, they know how stars are moving, the white dwarf that would come super close to another star so that it would cause a lensing event that would allow us to measure the mass of the white dwarf by how the light from the other star got bent around the white dwarf. So they identified this white dwarf, which is very bright, but white dwarfs are usually very faint, which tells you that it's a super close white dwarf. And this is a background star that's maybe close to the center of the galaxy, maybe 5 kiloparsecs away. So we took 9 different epochs of observation. So this is the first epoch. Here's the second epoch, and you can already see that the target star looks like it's behind the white dwarf. It's actually not completely behind the white dwarf, but it's hard to see at this stretch. So as we go through our different epochs of observations, you can see the other star coming out from the halo of the white dwarf now. And that I think is the last white dwarf image. This I'm showing at a different stretch. You can see the target star there. You can see the white dwarf coming close, coming close, coming close. Here, it looks like the target star is behind the white dwarf's leading column, which is a pane, and then here and then there. So basically, this shows you the event that we tried to measure. And what we want to measure is whether how much this star moves because of the presence of the white dwarf in between us and it. And it's a very precise measurement we have to make. We have to measure it by about 1 milliarc second, which is about 2/100ths of a pixel. And the challenge is that you can sort of see that the white dwarf isn't just a point in Hubble. The white dwarf has a profile, a point spread function that has a lot of features out exactly where we're trying to measure this star. So that makes it a complicated measurement, and you have to be very, very careful when you make these measurements.
So the white dwarf is the brighter one that is moving?
Yes, yeah, the white dwarf is moving, it's close to us. And so the light from this background star is being bent around the white dwarf, and that allows us to measure the mass of the white dwarf. And you can see the diffraction freights of the white dwarf. If you look at it in the frame of the white dwarf, you can sort of see that the little bumps mostly stay in the same place. The PSF bumps mostly stay in the same place. but not exactly. And the target sort of moves around the white dwarf. And so that's one way that I was able to sort of figure out how to subtract the impact of the white dwarf so that I could measure exactly where that target star is, not relative to the white dwarf, but just relative to the background of all the other stars in the image. So it's doing something relative to the other stars. The white dwarf is messing it up, but we don't want to measure it relative to the white dwarf because the white dwarf is moving like crazy. And so this shows you the deflections that we measured, which were pretty small, on the order of 1 milliarc second or so, but it fits the model very nicely. And it allowed us to put one point on this curve, which shows the relationship between the mass of the white dwarf and its radius. Now, if the white dwarf had a pure iron core, it would be way down here. But the fact is that it has a carbon-oxygen core, which is what we expect, with a certain atmosphere of hydrogen. And so by measuring this one data point, that allows people to go back and look at the models of white dwarfs to help us understand them better. But these data points take a long time. It takes a lot of work to get this data point, given that we had to wait for this experiment to happen. Nature is essentially doing an experiment for us. So one last point about this white dwarf measurement. In 1930, when he was 19, Chandrasekhar came up with the idea of white dwarfs. He said, at some point, when stars collapse on themselves, there's a limit to how tight they can get by putting all of their electrons together in one place, the electron degeneracy pressure. And then he said that the weird thing about this situation is that when you put more mass on it, it gets smaller rather than bigger. And so he won the Nobel Prize for this, and it's called the Chandrasekhar limit, which means that at some point you can't put any more mass on it. It's going to collapse into a neutron star. So that's what Chandrasekhar said. It turns out that Eddington, when they were in some public meeting, he thought this was a ridiculous idea. He said that there should be a law of nature to prevent a star from behaving in this absurd way, like you're talking about, Chandrasekhar. And it turns out that modern measurements of white dwarfs have confirmed exactly what Chandrasekhar said. And so Eddington kind of has egg on his face. And the measurements that we made confirm exactly what Chandrasekhar said. And the irony is that we used the experiment that Eddington used to prove Einstein right to sort of prove Eddington wrong. So it's kind of a poetic justice on this. And Eddington has been gone for a long time, but it's interesting how these big names sometimes have big egos, and sometimes big egos catch up with you. So the next thing I'll talk about is the measurement of the isolated black hole. Now, there are three kinds of black holes that we know about, or that we expect there to be. One is a stellar mass black hole, which has around 10 solar masses, maybe 5, somewhere between 4, and they could go up to 30, I guess. But they come from the product of one star's evolution in general. Then there are intermediate mass black holes, and these have maybe 10,000 solar masses, and nobody's observed an intermediate mass black hole. People for a long time thought globular clusters, since they're like little galaxies, they should have intermediate mass black holes at the center. And I've unfound at least one of them. Somebody claimed to have found one at the center of Omega Centauri, and I showed that there could be one, but not as big as the guy said that there was. And so there's no evidence for it. But people think that they should exist at the centers of globular clusters. And then the third kind of black hole is supermassive black holes. They can have 1 million to 100 million solar masses, maybe even 1 billion solar masses. So I'm going to be talking about the first kind of black holes, and we know that they exist, but we've only seen them in certain circumstances. So stars, this plot right here shows you on the x-axis, it's the initial mass for the star, going from 9 to 24 solar masses. And then on the y-axis, it shows you how much is left over after the star does its evolution. And so if a star between 9 and 18 goes through its evolution, it'll leave a neutron star in the end. A star like our sun is going to leave a white dwarf, but a bigger star between 8 and say 20 is going to leave a neutron star. But if it's much bigger than that, it's going to leave such a big remnant that a neutron star can't survive, and it's going to have to turn into a black hole. Now, there are different models that predict different initial masses relating to black holes and final masses, but it's roughly 20 solar masses. If you have 20 solar masses, then you're going to make a black hole and not a neutron star. So there should be a lot of black holes in the galaxy, just hanging around because we've had a lot of heavy stars that aren't there anymore. So a large fraction of these are expected to be isolated because a lot of them start as single stars. And if they're binaries, if one explodes, then the other is left alone. Also, often these things end up getting separated from each other. They could get a kick velocity when they're formed. So, but a single black hole has never been seen before because it's very hard to see them. So the detections that have been made of stellar mass black holes, usually they're found in binaries, like X-ray binaries. So you have a star that went through its evolution and created the black hole, and it has a neighbor. And once this neighbor grows and goes through the giant phase, it starts dribbling mass onto the black hole. And you can see the black hole because of what's happening to the gas that gets dribbled onto it. You don't see the gas when it enters the black hole, but the gas goes into the black hole and it hits other gas that's hitting the black hole. And that creates a hot spot that you can see. And a few black holes have been observed through radio velocity measurements, looking at binaries and seeing, this star is moving around in a circle. What's causing that? It would be a black hole. Also, some people have observed it with astrometry by seeing a star that's moving around in a circle, and you can't see what it's moving around. And you can say that that's a black hole. But all of those black holes are in binaries, and they probably have different formation mechanisms, and it's hard to do a census of them. Black holes, of course, have also been detected when two objects merge, like black holes, neutron stars in LIGO. I don't know if you've noticed about the gravitational radiation that people have started measuring, but they see 30 solar mass black holes merging with other 30 solar mass black holes and creating something big. And so those aren't isolated black holes, but those are another way to measure black holes. But microlensing, as far as we know, is the only way to measure completely isolated black holes. We can measure their masses, we can measure their velocities. We can say a lot about how many there are in the galaxy, which can help us understand, how the galaxy evolved over time. So let me talk about microlensing with finding black holes with microlensing. So I don't know if you've heard very much about microlensing. It's actually a very ground-based area of astronomy. There are two big projects, OGLE and MOA, which network together, and they observe millions and millions of stars every single night. So this shows you the center of the galaxy and all these little fields that OGLE just observes every single night. They take an image of that field every single night to see which stars are changing brightness, which stars might have had another star go in front of them, creating a microlensing event. So far, they've detected 30,000 microlensing events. So they've seen 30,000 stars get brighter because another star went in front of them. Most of these aren't very bright, maybe 10, 20, 30%, but they catalog them all, and that helps them understand everything that's in between us and the center of the galaxy, because you're not observing the stars that you see, you're observing what's in between us and the stars that you see. So the OGLE collaborations observes long events and short events, events that have low amplitude and events that have high amplitude. The high amplitude events are really what they're focused on right now, because they can show planets. If you have a star that's going in front of another star, and this intermediate star has a planet behind it, then the star will make a big microlensing bump, but then the planet will make a little bump. And you can study the little bump on top of the big bump to understand the planets that this intermediate, the star in the middle, in between us and the bulge, has. And you can do very interesting science with that. For one, that allows you to find planets that people can't find in any other way. People find radio velocity planets, they find eclipse planets, but eclipses they have to be very close to their star. So you don't find stars that are far away. Radio velocity planets, you have to have a massive planet because it's got to pull that star back and forth a lot. Whereas microlensing planets that you find, they can be cold, they can be small, they can be far away. So you find a very different kind of planet. So essentially you're doing a census of a different kind of parameter space with microlensing. And so it's in people that try to understand exactly what the typical other solar system looks like, or how solar systems form, or what the typical one is. They need to have information about the rest of the planets, and microlensing allows you to find the rest of the planets. In fact, there's going to be, the Roman mission is going to have a large component that involves microlensing so that we can understand the rest of the planets. In addition to these high amplitude events, there are also very short events, which could be related to just free floating planets. It could be that when the solar system makes planets, some of them get lost out into space and just float around. And if those little planets happen to float in between us and a background star, then it could make that background star blip a little bit. And if you can measure that blip, then you can measure something about free floating planets. The long events could also be caused by black holes. And so that's what I'm going to be talking about here. So if you have stellar mass black holes causing microlensing, it turns out that the light curve that you see is affected by 4 different parameters. One is the duration. You can measure that. It's affected by the distance to the lens, the distance to the lens, which is the star that is bending the light. And then the source is a star that's in the background that's having its light bent around the star that's in the middle. And then the velocity. So the relative velocity of the two affects the duration time. And it also affects what you're looking at. So if you know all 4 of these things, then you know the mass of the lens, you know the mass of the thing that's in the middle causing the bending of the light. It turns out photometry, we measure just the duration, the time it takes for it to go up and down. That's pretty much all we can measure with photometry. And people thought, well, if the events are long enough, then you have to have a supermassive thing in the middle, so it has to be a black hole. But it could be a fast black hole, or it could be a slow star. The duration time sort of, it doesn't have anything to do with how massive the thing is. It's also related to how fast they're moving relative to each other. So you need more information. So this is another plot that shows the astrometric impact of microlensing. So as the green circle is the Einstein ring for the lens, the yellow star is the lens. And so this blue star, or let's see, this
Circle, the red
yeah,
circle.
the red circle is the true position of the star in the background. And the red dot is the average position of the average apparent position of it. So let's see.
Dr. Anderson,
Yes.
can you stop the movie in the middle of it? Can you?
Yeah. Let
can
me
you
see
make-
if I can do that. Let's see.
I'm
yeah.
still trying to wrap my brain around what we're
Yeah.
seeing
Let
with
me
the
show
microlensing.
it. Let's see. Let me go back there. Hold on, let me go. Okay. Okay. So what we're looking at here. So this open circle here is the true position of the background star, and it's just moving straight in a line. It's not changing at all because it's just moving in a line. It doesn't know anything about the star that's in between us and it. It's just moving the way it's moving. So as I showed you before, the microlensing physics of light bending creates 2 different images. This one blue image here, and then this other image here on the inside, on the other side of the lens. So it just
So I think I understand why I see the blue dot on the right that's inside the circle.
yes.
I could sort of see the red circle coming and being bent around I can sort of understand why we would see something there. But why do we see the one on the left? What causes that?
It's just when you solve the equations for the transfer of light in a bent geometry, which general relativity says that space-time is bent by matter, then that's just what you get. That's the path that light takes. There's one
Okay.
path that allows it to go on one side of it and another path that allows it to go on the other side. And so,
Okay.
so basically the thing that you're supposed to take away from this is that the image of the star, which is this red dot here, is where it appears to be, which is like the average of this position and that position, is displaced, is not in the same position as the true position of the star. So if we can measure, we know where the star is supposed to be. If we see it early and then we see it late, we can just draw a straight line and know where the true position is. So if we can measure the true position and we can measure the apparent position, then we know how much the lens moved the star. And if we know how much the lens moved the star, then we know how massive the lens is. And so there are ways to find that I said that there were 4 things that you needed to measure if you want to measure the mass. You need to know how far away the lens is, how far away the source is. You need to know how long it takes, and then you need to know the astrometric shift.
Dr. Anderson,
Yes.
can I ask a question about the slide You
Sure.
just moved from, in the bottom graph, the previous slide that we were just
Yes.
talking about,
Yes,
is the dotted line where the 0 is that the path that open red circle is
that's
taking?
right. That's right. So,
That's the
yeah,
path
so,
that's taking?
yeah, let me play this one more time. Come on. Okay, yeah, so what I'll show you real quick. So let me pause it here. So the position, the apparent position of this background star
Mhm.
is moved. And it turns out that it's moved in the y-axis, it's moved away from, it's moved up this way. So that's the blue curve here. It's moved, the lensing causes it to appear to be farther away from the lens than it really is. So remember with the Eddington of the sun, it turned out that stars that should have been like super close to the sun's surface were actually appeared to be farther away. So we end up seeing things pushed away from the lens apparently. And so it gets pushed away when it's on this side, it gets pushed away when it's on this side, it gets pushed away in that direction. And when it's on this side, it gets pushed away in that direction. But all of the pushing in the Y direction is up because it's pushed away here, pushed where, pushed there, pushed there. But with X, it's pushed this way and then it's pushed that way. And so we can sort of look at how the star is pushed to verify that our models are right. And then if we measure that and fit it to our models, we can figure out how massive the star is. I know this is all very complicated, but it's also very cool to realize that, you know, Einstein figured a lot of this stuff out a long time ago, said, oh, this is useless because nobody could ever see two stars come so close to each other, but we can actually measure it. So there are ways to figure out how far away the lens is, and I'm not going to go into all of that detail. There are ways to figure out how far away the source is, like when you have a background object, you want to know how far away it is. You can figure out how bright it is, like what kind of star it is, and that allows you to figure out how far away it is. Often you're looking at the bulge and you know how far away the center of the galaxy is. So it's pretty easy to figure out how far away the background star is. So the next thing you have to measure is what is this deflection and fitting it with models. So let's see. So basically you don't just, you know, open your telescope and find this. The challenge in this is that people on the ground observe events that look like they're going to be really, really long. And when you see events that look like they're going to be long, Kailash says, okay, I'm going to observe this with Hubble. So he starts observing it with Hubble, taking one epoch, another epoch, another epoch. And at some point, it looks promising that maybe this is really a black hole event. And he starts taking more and more data. But it's not the kind of thing that you can set up the experiment and just run it. You sort of have to have someone else find something that might be good to look at. Then you have to get time to look at it. And then you have to follow it up and actually measure it. And we've followed maybe 5 or 6 of these things that we thought, oh, this is very promising. And it turned out not to have any signature at all. But this one happens to have a beautiful signature. So the challenge that we're trying to measure is we're looking at for a deflection of 1 milliarc second. So that's like taking a quarter in Maryland and moving it all the way beyond California. So you're trying to measure a displacement of the star by the width, by the diameter of a quarter at the distance of Los Angeles, which is crazy. But that's the kind of thing that Hubble does all the time. So that's the size of the effect that we're trying to measure. And the fact that it's often in a field that has other stars makes it harder to measure it. So the particular program that was successful, in 2009, we started the program. Kailash saw that these people were finding a very long event that could be a black hole. And so he started taking observations in 2009. The deflections are very small. They're about 1 to 2 milliarc seconds, and we need to monitor it for over several years. This is, like I said, one of 8 events that we've looked at. Here is the light curve that you see from the ground. So this whole time here is about 300 days. So this is about 1 year between when it goes from you can't see very much amplification. They observe it, they observe it, they observe it, and then all of a sudden it goes bright, and then it starts getting faint again. And if you zoom in on the middle parts, you can sort of see this curve that it shows there. All of these different data points, you can see not so many points on the left, but a lot of points on the right. that means that when people realize this is an interesting thing to monitor, everybody gets their telescope out and starts watching this event. So this was one of those events. And Kailash had to decide early, yes, this is such an interesting event. I want to throw HST time at it. Let's see what we can measure. And so we were successful. Here are some images of the event. When it was its brightest in August of 2011, you can sort of see that there's a background star. This star has nothing to do with anything. I really wish it wasn't there because it's in the way. But it just, you end up trying to observe things wherever they are. And sometimes they have bright stars that are just complications. So the target star is the one that has the arrow pointed at it. You can see in August 8th, it was bright. In October, it was getting fainter. September, it was getting fainter. And later it was getting fainter. And pretty much it stayed the same faintness level. It's maybe a factor of 220 fainter than the bright star that's next to it. But you can see around that bright star that's next to it, you have these little bumps of the PSF that I was showing you earlier. So it's a real challenge to make this measurement. And so as you can sort of see, here's the location relative to the PSF bumps where we have made the observations. And you can see that we have to measure a position right on this bump. And that is not a very favorable place to measure something. And also the PSFs change with time. The PSFs aren't exactly constant, so they change, and you have to make a model of the point spread function so you can subtract out this completely unrelated background star so that you can measure the target accurately. And so this sort of shows the subtraction that I did. I did all the subtraction and PSF fitting and stuff. So on the top, you can sort of see, here's one image with this is the target right here. And our goal is to subtract this whole halo of this star so that it's not affecting the measurement of this star. This is when that star was bright. But when the star gets fainter, you can sort of see that the halo features become just as important as the star itself. So this shows you how good a job I was able to do subtracting the halo features out so that at the location of the background star whose position I wanted to measure, it was measurable. So one interesting thing about microlensing is that all light is affected by this bending. And so it's a completely achromatic event. So if there's any change in color of the star when it goes through the brightening and then the faintening, then you say, okay, it's not microlensing causing it, because this is all just purely geometric and it has nothing to do with the wavelength of light. So we measured very carefully and showed that in fact, the star got brighter and fainter without any change of color. And from the ground, that was kind of hard to do because you had this bright star next to it. And it's very hard to measure the brightness of this target star next to this other brighter star. But we were able to confirm very well that it's completely monochromatic, achromatic. This is the setup that Kailash had to measure. The challenge with black holes is you don't see the black hole, so you don't really know what kind of path it's taking behind the other star. So we went through all the geometry and figured out that it's actually moving in a direction like that relative to the background star. Here are the deflections that we ended up measuring. So this is the deflection in the X direction on there, and the black line shows you the model, and the deflection along the Y direction is shown on the bottom there. And so we were able to derive the parameters for everything and say the mass of the object causing the lens is about 7 solar masses. We tried to measure whether there was any light coming from it, and it doesn't appear that there's any light coming from it at all. And so it is truly a black hole. So this is the very first solid measurement of a completely isolated black hole. But remember at the beginning, I told you something about name that tune, and that people think, well, I can make this measurement in 5 observations, or I can make it in 3, something like that. So it turns out that some people got impatient with us and they thought we weren't measuring these things fast enough. So they decided to measure them themselves. And they came out with a competing paper trying to interpret this event. And that's fine because the data that Hubble takes are public after your proprietary period. And you don't get a proprietary period for 10 years to reduce microlensing events. And so they came up with their own measurement, but it turned out that their data points didn't fit their model very well. And it turned out that they predicted that it might have been a black hole. It might have had 4 solar masses, but it might have also just been a neutron star with 1.6 solar masses. So they said, actually, it's not clear what this is at all. And so we were very, very certain in our measurement of 7. So we re-reduced the data again and tried to show what we did. Other people did independent analyses of our measurements. And there are 2 more epochs that the other group took. We've reduced everything and we're very confident in our results that it really is a black hole. It's an interesting way to do science, and that it's always nice, when somebody comes up with an exciting result, you don't usually get confirmation on it. You sort of just have to take their word for it. But this time, actually, 2 different groups made measurements, and I think they're going to come up with new measurements that agree with us. It turns out that where is this black hole? This is an artist's conception about where this black hole is relative to us. So if we are here at this red dot in the galaxy, and the galactic center is here, then obviously we're looking at this close to the galactic center, because those are the fields that get monitored for microlensing events. And it's pretty much, 20% of the distance to the galactic center. And it's actually in one of the spiral arms. So it makes sense that you would have some massive remnant in a spiral arm. So just for the future of microlensing, we're monitoring 5 more long duration events, any of which could be a black hole. Gaia very soon is going to be making a lot of these observations because it's looking at the whole sky. So whenever 2 stars line up and cause a shift, Gaia will be able to measure that. Roman, the new telescope that's going up in 2027, has a whole program designed to do this. And so they'll find black holes, they'll find planets, they'll find a lot of things. I'm going to be very involved in that. Rubin will also be able to identify them because it's going to be probing a large region of the galaxy every 3 days. I think it's going to survey the whole sky. And also the VLT can provide very precise position measurements of things. So let's see. So when we put our paper out there in public, a lot of people got very excited about it. And one of them was a journalist from Australia. And she said, this is her quote, was the black hole they found has a mass about 7 times the mass of the sun. That would make its event horizon just 42 kilometers. Take a moment to marvel at that. Scientists were able to detect an invisible object less than 1/10 the length of the Grand Canyon from over 5,000 light years away by studying the changing light of a more distant star. That's pretty amazing. So, and we're also answering, big questions in physics too. So it's a fun time. I'm happy to take any questions.
That's freaking amazing.
Yes.
That was truly amazing.
Oh, thank you.
So I have
Thank you.
I have a question. Maybe others do too, if I could. Sure. So can you use microlensing and look at something that is already so there are other ways to know that there, as you mentioned earlier, there might be these other techniques that are used to determine that there's a black hole somewhere. Can you use those kind of known objects and use the microlensing technique on them to see if, to corroborate the microlensing?
The challenge is that they would have to pass in front of something that's behind them that you can use as a probe. And that's the real challenge that Einstein said, that he said we would never see it because you have to have 2 things that are lined up so perfectly. And so that's the real challenge. We have to sort of wait for nature to set up this perfect alignment of things, or near perfect alignment. You've seen in extragalactic things, you see a supernova go off behind a galaxy and have 4 different images of the supernova. You need some sort of a perfect situation like that.
I see.
Yeah, I have a question. You just mentioned these other telescopes, particularly Gaia and Rubin. And since they're looking all over the sky, are you going to have a problem knowing the distance to the light source?
Yeah, so
you were able to assume the center of the galaxy for this one, but what about if you're just looking at a random direction in the sky?
Yeah, that's a good point. Gaia has parallaxes for a lot of objects, but it doesn't, obviously there's a limit to how far away it can measure parallax. Often you can look at the star's color and brightness and figure out how far away it is. That's called spectroscopic parallax or photometric parallax. So, that's one way you can figure out where the background star is. At some point, if it's really far away, it almost doesn't matter how far away it is. It's almost like it's infinitely far away.
Okay, thanks.
So I have a question. You said that Nancy Grace Roman is gonna possibly give you more data information about where you might find a black hole, or how is it gonna help
So,
with the micro lensing?
yeah, so that's a good point. Roman is going to have a dedicated program. It's going to spend maybe 2 months out of every year for like 4 or 5 years observing the exact same field with Hubble type precision on astrometry and everything else like that. And anytime that there is a black hole crossing through any of its 7 fields or so, that black hole is going to perturb the positions of stars. So we're going to be able to just look at the positions of stars getting perturbed. And it turns out that a lot of things are affected by astrometry that aren't affected very much by photometry. So even if they just brighten by 1 or 2%, you can actually see an astrometric signal that's significant. And so Roman is going to be able to just detect lots of black holes that we couldn't detect any other way. And then the one also nice thing about it is that you don't, with this, we sort of had to have a trigger. We had to sort of see things ramp up and start getting brighter and then say, oh my gosh, let's start observing. And you're almost too late by the time you realize that it's something interesting. With Roman, they're going to be just observing everything for 5 years. And so whenever it starts or stops, you know, they're able to sort of look at it in the past and the future.
Okay, thank you. So there's going to be a lot of data coming in from.
There's going to be a
Nancy
crazy amount of
Grace.
data, especially in
Yeah.
these fields, which are going to have, you know, 1 million stars in each set of images.
Wow.
But you need to have millions and millions of stars to have a few that overlap in interesting ways.
Right. Thank you.
Sure.
Thank goodness for AI. We'll be able to analyze all that data.
I have a question.
Or just make it up.
Yes.
Still with me?
Go ahead, Dave.
Yeah, the question I have, it's amazing that you were able to measure the event horizon at 42 kilometers from 5,000 light years away. But I was wondering about the sense is, I mean, was that the expected the expected measurement on that event horizon, or was that smaller than you'd expect? To me, it seems like a very small
Yeah,
event
well, I
horizon
mean,
for
that
something
just
that massive.
describes that just comes directly from the mass of the black hole. So the fact that we were able to measure the size of the event horizon tells us that we measured the mass of the object. And it didn't tell us that it was a black hole. It just said that you measured something that has this event horizon size because it caused this deflection. And then you have to rule out what else it could be. You had to rule out the fact that it couldn't be a luminous star because we would have seen it. You had to rule out the fact that it couldn't be a planet because it couldn't be that small. So you had to rule out a lot of other things that it couldn't be before you could say for sure that it was a black hole.
Thank you.
You're welcome.
Do we have any other questions? Well, I would just like to say thank you so much,
Oh, you're welcome.
Dr. Anderson. That was just amazing, amazing presentation. Very, very cool.
Thank you. I hope I pitched it right. It seems like most people understood the basic background.
Yeah, well, yeah, we have a lot of geeks in the club.
There's a multiple choice test after the meeting tonight. Watch your email.
Well, that was really cool. So
Okay, thank you all.
Is that presentation going to be available on the website, your presentation?
I could send it, yeah.
I'm an astronomy teacher. I just texted you private. If you're willing to come talk to my students, I teach in Glen Burnie, Maryland.
Okay, I could probably do that sometime.
And I can get your email from Victor if he's willing to give it to me.
Yeah,
You
that's
can-
fine. Yeah, go ahead. Yeah, Victor, feel free to give it to her.
No problem.
Thank you.
Okay,
Nice to meet you all.
I'm going to, if I can, take over sharing the screen again. And go back into presentation mode. Are you guys seeing anything?
Yeah.
What are you seeing?
We're seeing your,
refresh your desktop.
we're seeing your screen in normal production mode. You just need to blow it up into presentation mode. There you go.
Right.
And now switch it to the other one. Yeah, there you go.
Okay, once again, thank you so much, Jay. And you're welcome to stay on or not if you need to get going.
Yeah, I should probably get going. It's very nice meeting you guys.
Yeah, thank you.
Okay, yeah, again, thanks.
Thank you.
Thanks very much.
Okay, so I'll just keep going with the agenda for tonight. The next section is our what's out. And we've got solar, shallow sky, and our space-based stuff. So we'll go through this stuff quickly. Phil, you want to go ahead?
Yeah, so I kind of skipped this month and talking about what's in the news. There is so much, so if you track this stuff, what's going on with the sun, especially since this is such an active cycle relative to a previous cycle, you see that there's things in the news all the time. And one of the reasons it's there is because of the technology that we have monitoring it with the SDO, which is the Solar Dynamics Observatory by NASA, and that's observing the sun full time from outer space. And it comes up with new data all the time. And plus we have the Parker Solar Probe mission underway, which is also constantly sending back information. Not only count, and then you count all the ground-based terrestrial telescopes and ways of observing what's going on. And there's always a lot of questions as to what's happening here. So this is kind of like a teaser for the Astro School. And to where we're going to dive right into what's going on and explain what's happening with the sun, because what I want to do is really address common questions about the things that we could visibly see and how we see that. And so what I did is, this is a picture I took, as you can see, in October 25th of 2014, which was the largest single sunspot cluster of that particular cycle. And it just happened, I got a really great picture of it. And it just so happened, if you see this picture in Sky and Telescope from time to time, it's not my picture. It's the one that NASA took. And when I did the research, we took it within an hour of each other on the same day. And it was, so that's why when I looked at it, I thought it was my picture all of a sudden at first, because it's exactly the same in every way. And in some ways, the one that I published had less detail than this one. But it's a great one to show the different areas of what's going on in the sun. My arrows are a little off on a couple of things here, but when you look at sunspots, and when we're looking through a white light filter, so there's different ways, different types of filters to visually look at the sun. And then there's other types of filters that you should never use, like calcium K-line filters. That is not for visual observing. That's for photographic only, and you could hurt yourselves if somebody had that set up with a calcium K-line filter. It's not for that, but we talk about that stuff during Astro School, and that's something that an amateur very rarely has. They're expensive, and you got to know what you're doing. But so here, what I've got here, Justin, we're not going to dive into this because I only have a couple of minutes here to talk about this, and you can certainly view it online and other areas. But what's going on here is I've identified all the different structures that go on inside the sunspot. And some people think when you're looking at a sunspot, it's the contrast between the spot itself and the photosphere. And the photosphere is the layer that we generally call the surface of the sun. And you could see what's going on there. But when you look at it in hydrogen alpha, which is the chromosphere, which is the layer above the photosphere, it looks different. And the reason that it looks different is because you're actually looking at a different feature. So in this particular area here, I'm going to, Victor, could you go forward 2 slides for a second? Go to the next one. There you go. Push down the down button one more time. I think it'll build. There you go. Just leave that. And then to show you, when you look at that sunspot group, how big that is. This is an image I showed a month ago for a different event that we monitored at one of our club events that we recently. And that going across the middle is 110 Earths. That is, the measurement of what the Earth is in ratio to the sun. So I call this for perspective. So now, Victor, if you go back 2 slides, you're going to just see how big that sunspot grouping is. It is tremendously massive. And the reason that those areas are, the dark area there is darker than what you see in the photosphere is contrast, because the photosphere is 6,000 degrees, approximately 6,000 degrees Kelvin, and that sunspot is approximately 4,000 degrees Kelvin. So it's much cooler, even though it's still hot enough to cook an egg on, but it's much cooler, so it appears to be darker. And what's going on there, if you go to the next slide. So this is some pictures I took on October 26, 2013. And the reason for the size difference is that there was different size aperture in the telescopes. That with my white light filter on my 5-inch refractor, which is about 130 millimeters compared to 60 millimeters of the photos of the chromosphere with the H alpha. But the features are lined up exactly. So not only do you see a different detail, but if you look basically where AR 1877 is, and then go over to the other area, which is in the, right there, perfect, dead on. So if that was blown up to scale, it would still not look like what you're looking at here, because what you're looking at on the left side is a photosphere effect. And what's happening there is there's a loop prominence, I'm sorry, a loop magnetic field that's coming through there, and is coming through that hole in the photosphere. And actually that magnetic loop is hitting into the photosphere. And that's the reason that things look so differently when you're looking through the top and you're through with the different telescopes. And there's also crazy things that happen with the positive and negative charges in these magnetic loops that are very complex. And there's I forget the study that was done way back early in the 20th century where they identified these kind of things. This goes back, to the early 20th century. And it's just amazing that they were able to figure this stuff out and detect it. And that science is holding up today as being still accurate. And there's all kind of study what's happening here. So when we go into Astro School and stuff, we're going to dive deeper into this. And just to kind of build off of Crystal, when Crystal was showing this book here, which she's right, this is really an excellent book for beginners and beyond. There's another one. I'm going to push this into chat right now. You guys can take a look at it at your leisure. It's this book right here. This book is not for the beginner, but it is the most. It is the most. What's the word I'm looking for? It's
Comprehensive.
comprehensive. There you go. Taking $1 out of petty cash. It is the most comprehensive solar book that you could humanly read. In other words, it's not all formulas and stuff, but it is fantastic. This is a book that's created in Europe as part of the French Astronomical Society. And it's put together by 14 authors. And it's just amazing. I mean, I've got a bookshelf full of books about the sun and everything else about it. And this is unbelievably good. It's also pretty expensive. Right now, with the exchange rate, it's a little over $80, and you can only buy it from the author in Europe. But it's just amazing, and I'll be using that as tools to help show what's going on. So I just wanted to introduce everybody to this, and moving forward, I'm going to just pick on certain features. But once again, for the Astro School that we'll do in July will be the classroom session. And then we'll go out into the field a couple weeks later and do the lab session where everybody could physically see what's going on. And I just want to say that so the hydrogen alpha is a different kind of filter for measuring, for observing and imaging the chromosphere, the white light filter you use for the photosphere. And then, Victor, if I could just bother you one more time to go back to that first picture. There you go. If you look really closely at that, you can see some granulation in the photosphere. If you get away from the sunspot and go through there, well, the granulation is incredible to watch and to understand what's going on. And I just took delivery this week of the brand new Herschel wedge from Bader, just came out. And when we put this on my 5-inch refractor or the 4-inch refractor, we're going to see detail in the sunspots and detail in the granulation of the photosphere like you've never, ever seen before. And I'll have this out, when we go out for daytime events for observing the sun. So I'll have different, 3 different filters, and you could do all kinds of different observing for pleasure or for science. So with that said, turn it back over to you, and I think Wayne's up next. So thank you very much for
Awesome.
questions.
Phil, everybody knows the term lunatic, but you're a solatic.
Yeah. And
And you're gonna love the presentation that we have coming up next month too. We have space weather, NOAA, and you'll hear some interesting stuff about the.
I'll have to watch
the
it
sun.
because I'll be out of town. But
Can I ask Phil a question?
Sure. I'm sorry. Go ahead.
Thank you. Phil, I'm primarily solar. As a matter of fact, if you look over my shoulder, that's a wedge on a 4-inch
there you go.
and a hydrogen alpha, the Blunt 50. Is there any such thing as a solar impromptu?
Yes. So basically, that's what this Astro School is going to be. It'll probably be towards the very end of July on that Saturday. And it's basically a solar impromptu.
I meant for the members.
We used to do a Company 7, which is this telescope store in Laurel, on
Right.
Saturday, early afternoon, like from noon to 2. We used to do solar Saturdays. We were doing that. We're just getting together there for people to come together with solar scopes. But now that we have a lot of people interested in this, and we had some nice turnouts before COVID when we were all getting together for our event that we did there. So yeah, so we could start this anytime. You don't have to be at the observatory to do solar, but the benefit is that we could all be together.
Correct. Okay,
yeah.
thank you.
Al, I'm not sure if you were on at the very beginning of the, but there is an event coming, a solar event coming up at the Robinson Nature Center this Sunday at 2 p.m. There's a.
Yeah, no, I did get the email. Do they need more than what they?
There will be room if you want to come out with your solar telescope. We're up on the green roof there, which is just to the right of the front door. You'll see all the setup. Get there an hour to an hour and a half ahead.
Okay.
That's it. So
Okay. All right. Thank you.
Jim?
All righty, get myself unmuted here. So sometimes you look for a way to try to get like the high level view of what's going on, kind of get an appreciation of almost like the celestial dynamics that's going on, especially when we look at solar system objects. And I don't know how many of you subscribe to Sky and Telescope, but in your January issue, they always include something that they call the Sky Gazer's Almanac. And probably, I'm guessing a lot of folks probably just, don't give it much of a second look and maybe toss it out. But it really, and I don't look at it certainly, every month, but there are times when I pull it out because it can give me a good idea of what's going on. Can give you a really great high level summary of what's happening. Mouse click, please, Victor. It's also part of the HAL trivia that originally this was published by Paul Watson of the BAS, Maryland Academy of Sciences, and he called it the graphic timetable of the heavens. And this was like back in the 60s and 70s when he kicked this off, I believe. And you could buy it, and it was larger than what is coming out in Sky and Telescope. And it was almost de rigueur that you had to, if you were an amateur astronomer back then, you would buy one of those. And I think I heard Joel mention that we actually have like a copy of one of those that we're looking to get framed to maybe hang in the HAL Observatory.
That's correct.
So like BAS, Maryland Academy of Sciences, is kind of like we kind of grew out of that, HAL did back in, I guess, the late 90s or early 2000s. So, this thing here that you're looking at is actually a little bit of our unique history, kind of, one of our members way back when actually originated this thing back before there were computers. I mean, he would do a lot of this stuff, it was intensive work getting all this correct. So next click. So if we zoom in on just like this upcoming month, from about here till the next meeting, there are some things that this chart can show us. The first thing is you look at that very ice blue thing there, that's Venus. That's when Venus is going to set. And where the arrow is pointing, this is where it intersects the end of twilight. So twilight, as you can see, we've obviously, that little arc there is peaking around the 25th, the solar solstice, and then it's going to gradually start, curving back down. You can see that Venus is on a fairly steep incline here, so that within a month, it's going to have set by the time that you have the end of twilight. And compare that to a few weeks ago, where it wasn't setting until midnight. So, and this, of course, is because Venus is now racing to cut between us and the sun to head into inferior conjunction. So its apparent size is going to increase as it swings closer to us, and its phase is going to change from almost half phase, a little less than half phase now, into a crescent over the next few weeks. Next click. So the chart also, here's Mars, the red line. You can see that Mars is also going to do the same sort of thing. Now, you can compare the Mars line and the Venus line, and you see that Venus, because it is much closer to us, its speed is much more apparent. The angle of that is a lot steeper there. Mars is more gradual, but yet also within about a month, Mars is also going to be setting at the end, pardon me, at the end of twilight. So we're also pretty much at the end for the apparition of Mars, and it'll be several more months before the next apparition starts. Next click. What we can also see on this chart is where they are close together. That would imply also that they're potentially close together in the sky, because obviously being planets, they're going to be along the ecliptic. And if they're setting relatively close to one another, that means that they're not that far away. So the other thing that this chart tells you is that, okay, we got our closest approach of Venus and Mars probably right around now into early July. And then as Venus makes its swan dive towards inferior conjunction, that distance is going to grow apart. So you're not going to have a really nice tight conjunction of these two, which is a shame. But, still over the next couple of weeks would be a nice time if you want to get a picture of Venus and Mars together. They're probably going to be 3, maybe 4 degrees apart. Next click. And then our innermost planet, Mercury, we can see here it's going to make an appearance, but also, again, this is when Mercury sets. So you can see this is not going to be a particularly great elongation of Mercury. It's going to set well before, 2 hours before the end of twilight. Of course, it rarely would get to the point of it setting at twilight, but it's still going to be fairly bright. So if you want to check out Mercury, you can see that towards probably close to near the meeting next month, Venus and the Mercury line intersect, which means that those two will be very close in the sky. So that would be an opportunity to grab your binoculars and check out our innermost planet paired with Venus, because Venus will still be very bright and it'll be easier to sweep up with binoculars. So looking at, something like that chart, don't throw it away. When you get it in January, tuck it into your bookcase somewhere, and you might just pull it out occasionally and just kind of get a high level view of what's going on. This is really a very good resource. All right, next click. Oops, sorry, one more. So Saturn is actually starting to come onto the stage now. So we can see that, again, by the time our next meeting rolls around, it's going to be rising around 9:30. So that's much better than where we are now, where it's rising, a little after midnight. So, we're setting up for Saturn to have its opposition, I believe, in late August. So it'll become, instead of you having to stay up to a crazy hour of like 2 or 3 in the morning to get a good view, it'll be a bit easier. You might have to only stay up to around 11 or so to start to get your first look at Saturn for the season. All righty, next slide.
Does this mean Saturn and Mars are going to be very close together in the sky? They're just happen to be at the same time that they're both.
Well, the Mars line is setting, the Saturn line is rising. So it's at that point where the arrow's pointing, it's going to be a point where as Mars is setting, Saturn's going to be rising. So they're going to be
Okay.
180 degrees apart.
I see. I think this is amazing. I want to get the Sky and Telescope now just to get this. And or we should go over it every month. We should just slide the thing down one thing every month.
Well, I may very well be doing that. I don't know, but I would love to see us get like that original in the observatory. I think that would be so cool. Okay, so let's talk a little bit too about Saturn. I know that Saturn's been a focus, that Bob did the Astro School about it. So, but if you're interested in getting, behind the eyepiece and taking a look at it, again, it's a little early in the morning and that's a pain, but you can get a really nice view right now because Saturn was just at what we call quadrature. And quadrature is basically when you kind of have that right angle where, you take a line out to your target and you take a line over to Earth. And when it's making a right angle, that's quadrature. So another kind of way of looking at it is that as the sun comes up, Saturn would be at its highest point. It would be on the meridian. You can have the opposite. You can have a quadrature where just as the sun sets, the object is on the meridian. So we're just past quadrature for the morning. And what's good about quadrature is that it really helps you to see the shadow play on Saturn. Next click. So basically, when we're out here kind of like over on the edge, you get the chance to almost kind of like peer behind. You kind of get a little bit of an effect where you can see almost behind the planet a little bit. So at opposition, when we are straight on, so in other words, when that blue dot, which is us, would be intersecting the yellow line, you're not going to see the shadow on the rings at all. Okay, it's going to be totally obscured by the globe and you won't see it. But at this point in time, it has its really greatest effect. You get to see the most amount of that shadow of the globe being cast on the rings, which really helps give that nice 3D effect. The thing that is just so, I think, wowing about looking at Saturn in an eyepiece is just seeing how those shadows kind of make things kind of pop in relief. Next click. So if you want to go out and look at it and look for it, you really don't need a large telescope. I think 80 millimeters and maybe even smaller. It'd be interesting to see if people can pick it up in things even smaller than 80 millimeters. You need a little bit of magnification and some, steady skies, but you'll be able to see that shadow. And then the interesting thing is after opposition, the shadow will reemerge on the other side as we start to swing around the other way. And right now, the way that the rings are tilted, because they're in such a position too, that we're getting very good delineation of the shadow of the rings on the planet. So along the bottom part, the southern part there, you'll see the shadow of the rings against the globe. And then on the top part, it won't be as intense, but it'll be a little bit of a shadow. And that's kind of because you're looking through the crepe ring or the C ring, which is a little bit like a semi-transparent ring. And you're looking through and being able to see the rings also below. So again, it gives you this really, as those brighter rings cut across the planet, it really makes it just pop because you've got this shadow effect on it. So, my encouragement is, set the alarm on a morning and get up and take a look at Saturn now, because it's just a really stunning, beautiful object. And right now is a great time to look at it. And I think that was the last slide that I had.
Yeah, that's awesome. Thanks. And never ever even occurred to me that you'd be able to, that angle is enough to see anything. Thanks. Okay, Wayne.
Okay, as you can see from the title tonight, our What's Up in Space is all about acronyms. So GRB boat. GRB is how astronomers abbreviate gamma ray bursts, which are immensely energetic explosions that have been observed in distant galaxies. Okay, we've never seen one in our galaxy, and that's probably a very good thing, as you'll find out in just a minute. So we see them in very distant galaxies. Generally, there's two types of gamma ray bursts. First, you have short gamma ray bursts, where the gamma ray burst itself lasts for less than about 2 seconds, from less than a fraction of a second to about 2 seconds. And the surprising other kind is called a long gamma ray burst, which are greater than 2 seconds in duration and can go up to a few hundred, maybe even 1,000 seconds. So 2 seconds to a few minutes. So short gamma ray bursts are thought to form by the merger of two neutron stars, and long gamma ray bursts form from the collapse of a massive star. And in both cases, a black hole is formed. So the BOAT acronym is actually is a play on the athletics GOAT acronym, and this means brightest of all time. So we're talking about the brightest gamma ray burst we've ever observed. And this all comes from a paper released in early June from O'Connor and all his co-authors on a structured jet explains the extreme gamma ray burst with the great name of 221009A, which is actually just an encoding of the date which it was observed on. So 2022, October 9th. Okay, so this gamma ray burst was again observed in October of 2022 by the Fermi Observatory and also many other spacecraft, including Swift, NuSTAR, XMM Newton, Hubble, JWST. Lots of observatories got in on the act. And the this gamma ray burst was so bright that even at its distance that they've determined to be 720 megaparsecs, or 2.3 billion with a B, light years, it affected the Earth's ionosphere much like a solar coronal mass ejection. Sorry. So from 2 billion light years away, the gamma rays from this object caused issues with our ionosphere. So if it had been as close as someplace in the galaxy, we'd probably all be dead right now. And over on the right, I show an image taken by the Swift in the X-ray, the Swift satellite in the X-ray, which shows some expanding X-ray scattering rings that are caused by scattering off of dust inside the Milky Way galaxy. If you notice the scale I mentioned in the caption there, the rings range from 2.5 to 7.5 arc minutes in radius. And since I didn't say it, but this image was taken starting about 40 seconds after the gamma ray burst was detected. If it had been at 720 megaparsecs, to get out to 2.5 to 7.5 arc minutes, those rings would have to be expanding way, 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 way faster than the speed of light. So it's obviously something much closer to the Earth than the gamma ray burst itself. So the gamma ray bursts, gamma rays, of course, are electromagnetic radiation with very, very short wavelengths and therefore very high energies, much higher energy or shorter wavelength than visible light. But the lower energy afterglow, which means longer wavelengths afterglow, stayed unusually bright in this burst for many months. And this event seems to be different from almost every other gamma ray burst I've ever observed. And the authors took data from a lot of places, but primarily from the NuSTAR satellite. And they did some modeling of their light curves over time. And that modeling suggests that the jet resulting from the gamma ray burst was wider than other observed jets. So you think of a jet as being a very focused, narrow stream of relativistic particles coming out of the black hole from material falling in on it. But this one seemed to open up into a much larger cone. And they suspect, and their modeling shows that the best way to explain this is that the main jet drags stellar material out with it over an extended time, and that kept the brightness up in the lower energies or longer wavelengths. And I want to point out that contrary to the science fiction depictions of stars collapsing into black holes. The star doesn't just simply disappear when the collapse happens. Only the core of the star itself does the collapsing, and the rest of the star, its atmosphere, is still there. So the star wouldn't suddenly just disappear like they show in science fiction. There's also, of course, when the collapse happens, like it causes shock waves, and there's a rebound shock from the core collapse that then propagates back through the remaining outer layers. This is basically what happens when a supernova explodes. And that the shock waves propagating out then heats the material and cause light at many energies and to be emitted. And this contributes to the afterglow. So I thought this was really interesting because of the brightness of the gamma ray burst. To think something that far away could affect the Earth's ionosphere is in a detectable way is just absolutely mind-boggling. And also that the observations then provided details about what the actual jet looks like, even though we can't observe it. And with that, I'm going to call it a day.
Yeah, that is awesome.
Question, Wayne?
Thank you.
Okay, Joel?
Yes, I certainly don't want to jinx us, but how did the Milky Way get so lucky that we haven't? I mean, the gamma ray bursts, they're not that uncommon. Why haven't we had one close by?
Primarily because the gamma ray burst is a very directional thing. Okay, if you're not looking straight down the jet, you're not going to see it. Okay, so it's a geometry effect in addition to a distance effect.
So I'm not only asking about observational, but effects of what you say when we've detected this one from billions of light years away in our ionosphere. If there is one that we can't even observe within our galaxy, then we would be measuring even higher levels or potentially lethal levels.
We would, but again, the jet would have to be pointed directly at us, and we would A, see a gamma ray burst, and B, the gamma rays would do nasty things to us.
Okay.
Think of it as like a laser pointer.
It's right. Okay.
Yeah.
Now I'm saying it's not multi-directional. It is
Right.
only the direction of the jet.
It's
Got it.
basically bi-directional. You get
Right, bi-directional.
jets out the
Yeah.
both poles of the black hole, basically.
Great. Excellent. Thank you.
So it's like a Sith laser pointer.
Yeah.
Yeah, Darth Maul. Yeah.
Darth Maul laser pointer.
I know.
Those are both sides.
But well, Wayne, when you said it's like think of it like a coronal mass ejection, like half of one, right? Because coronal mass ejections are only going one way. But for the ones that you see blasting off to the side, they're not going to harm us because they're going there. If you could see them off to the side, they're not coming at us. It's the one when you're looking at it and it comes bright white and that's all you see, then you know it's coming right towards Earth. So this is exactly, if I'm understanding what you're saying, this is except for the one going right and one going left, or straight forward and straight back. This is the same concept, right?
Yeah, it's the same concept. You're right. That's a good analogy.
All right. Well, thanks for that, Wayne. That's pretty cool in the news stuff. So I think we don't have that much time left, so we can just go into the images. So Jim, are you still on?
I am. So this was taken 2 weeks ago. Was down at the shore with my sister, and it's a little bit darker down at Bethany Beach. Not maybe we got Bortle 7 there. I don't know. But that evening we had Venus kind of aligning with Castor and Pollux, and you of course have Mars, which is dead center there, and you can barely see it, but it was right at the beehive clusters, about on the outskirts. The next night it would actually be within the beehive cluster. So that's just simply throwing a camera on a tripod and taking a couple pictures and stacking them in Sequator. Was pretty happy the way that turned out. Next slide, I think, is mine. And this was also taken with the camera. Again, a little Canon with a telephoto lens on it. I think this was multiple 2-second shots. It was only, I think, like a 55mm telephoto lens. And so here's Mars on the outskirts of the beehive. And it's just really nice. You know, it's low tech, just through the camera and the tripod in the car. When I went down, certainly didn't, you know, couldn't be taking all my equipment down and anything. And yet, you know, was pretty happy with the stacking software that's free and available out there. And, you know, able to get a nice little picture of Mars visiting the beehive cluster there.
Beautiful. And along those, thanks. Here's another, is Stephen, are you on?
Yes. Yeah.
So you had the same idea.
Yeah. Of course, the moon was fairly bright, so the sky background was a little bright for me. But and the last one, I didn't have a whole lot of time to fool with the last one because I had to get up at 3 o'clock the next morning to catch a plane. So, but we did have fortunate to have halfway decent skies for 3 nights. So that shows Mars moving through the beehive.
Awesome. That's with your hyperstar, so
right.
That's a pretty much narrower field of view here.
Well, the hyperstar is about a 2-degree field.
2 degree, okay.
Yep. Yep.
Nice.
F2.
Michael?
Evening, everybody. This is with my 6-inch Newtonian. I was taking the Hercules globular cluster here and playing with some different processing software. So I was really trying to get, there's a little blue star in the bottom center there to pop out. And some monitors, it seems it really comes out with the red star right above it, and some not so much. But in general, I thought the globular turned out pretty good.
Nice. You gotta look for some of the core Hubble pictures that we were looking at earlier. Maybe you can do some micro lensing and see what you see there. And then this is also you, Mike?
Yeah, so back in April, I was trying to image M101. And so with the supernova that popped out, I thought, well, maybe I can go back and look and see if I image now and compare to before, can I actually see it? Is there a difference kind of thing? So the image on the left, I took a little bit of the stacks that I had, put those together. And then I took about 20 minutes or so. This was when we were getting some smoke from Canada. So it's a little tougher to see, but you can kind of see I try to highlight the before and after there. And that bright star that you see is not the same as that bright star on the left. That the bright star on the left is actually this guy here. Yeah, is actually this guy up here.
Well, that's awesome.
Yep, and same scope, same setup.
Nice. Something happened to the resolution when you sent it to me, so I'm sorry if it's not showing up as nice on the screen as the original. But all right, let's move on. Grace, are you here?
I am here.
This is so spectacular.
Thank you for the kind words, Victor. So last month I took a 2-week vacation out west to Arizona, New Mexico, to do night sky photography at a number of dark sky sites, as well as visit some observatories. This particular picture is taken from a place in central New Mexico called La Ventana Natural Arch National Monument. And it's about roughly an hour sort of southwest of Albuquerque, give or take. And the actual arch in the picture is on the right-hand side, just out to the right of that prominence you see there. Yeah, that's the arch right there. And so these are pretty dark skies. I had a meter with me, and I think it was reading it somewhere between about 21.5 and 21.6. So that definitely facilitated the picture taken. This is a panorama of 4 panels, and taken with my Nikon Z7, which has been astro modified using a 20 millimeter Sigma f1.8 lens. The Sigma lens is designed for Sony cameras. I have something called a Mega adapter that allows it to be used on Nikon cameras. I believe the ISO here was about 3200. And this is an 8-second exposure. And this is a stack of 10 lights and 10 darks that are first stacked in Sequator, and then the remainder of the processing was in Lightroom and Photoshop. This was one of about, I think, 7 different sites I was able to visit to do some night sky photography. So it was a great opportunity.
Grace, I agree with Victor. I want to pipe in that it is fantastic.
Thank you.
You know, and these are the kind of things we like to show it, like in Astro School and stuff, to demonstrate how you do those lights and those darks and get this composites. Because, you know, if you've never done this before, and if you know that you don't know, just this is challenging, and it's fantastic.
There's so much going on in the photo. It's just, I love it. Is there, what is the lights that are down in the lower left? Is there a town or something?
I don't think that's a town. This was taken fairly late in the night. It was around 2:30 or so in the morning, maybe a little later than that. So it could be some early parts of, you know, solar activity, or it might be some stuff in the background. But yeah, well, it's possible. There were towns within about a 20-mile drive of there. The biggest one is a town called Grants, New Mexico. That's where I was staying at the time.
It does look like you picked up some air glow that's
Yeah.
those linear streaks. But I don't know, that does look like light pollution there, just
Yeah.
to the right of that tree. But other the higher stuff, I think is air glow.
Yeah, I think you're right, actually.
There's probably a German word for it. It's Geigenstein or something. Well, that's just awesome. Thanks for sharing that. And James isn't on, but he had a few photos that I thought were amazing. He also got Mars in the cluster there, and I thought this is a pretty amazing photo. I don't know anything about the details, but James shared it. I think he has the details on his some of the links that he sent, but I didn't record them. And then he also mentioned in one of the emails that he drove to Ocean City and took some photos of one of the sunrises. I just thought this was an amazing photo as well. So with that,
Hey, Victor, real quick on James, you know, he doesn't come to these meetings, but if you ever have the opportunity to go out with James when he's doing his imaging and you see what he's doing and you see how simple he makes it look, it's just amazing. He sets up incredibly quickly. He's got a tablet where he's monitoring the sky constantly in real time. I mean, like constantly. And he's so quick at this, and he makes it look so effortless. And he just keeps coming out with the spectacular stuff.
well, it is. I mentioned to him in the email chain that I'm glad this is the sun and not some apocalyptic event. So. Anyways, so that's all we have for our meeting this month, and I hope you enjoyed the HAL meeting. I thank you all for coming, and I hope that we get to see more of you at some of our events. So thanks, and thanks for being part of HAL.
Thanks.
And I'm gonna stop the recording, and again say thanks, everybody.